All right, let's do this. We are actually going to take a page from middle school today, and you did probably a couple units and a couple different grades on transformations. We remember those units, transformations. We are in the unit of congruent triangles, though, so how does transformations factor in? Well, what we're going to talk about today are transformations where the triangles remain congruent. I do not change the size or the shape of these transformations that we're going to talk about. All right? These transformations, though, are going to be referred to, and it's at the top of your page, as rigid motions. This is a vocabulary term we will discuss throughout the year, because not only are we going to do transformations today, we have a whole unit dedicated to transformations later on in the year. All right? So a rigid motion is some transformation where the triangles remain congruent. Right? There's three in particular that you're familiar with. The first one is a reflection. If you think about it, and I can't physically flip this triangle on the board here, but if I flip the triangle over, am I changing its size or shape? Absolutely not. If I flipped it, it remains congruent to the original, so that is why a reflection is referred to as a rigid motion. All right, a rigid motion. The second transformation that produces congruent figures is a translation. Everyone ready? Let me do it with two, actually. Can I duplicate this one? You're darn right I can. Everyone ready? Are those two still congruent? Still congruent, right? What if now I turn it, I rotate it? It looks different, but is it still congruent to the original one I had? Yes. Okay, so these three up here are referred to as rigid motions because the triangles remain congruent. If you remember, you probably did a fourth one back in the day, a fourth transformation. And why isn't dilation up here? Because it's not going to be congruent to the original. I'm going to enlarge it or reduce it. So a dilation is not considered a rigid motion. All right, everybody good? Questions? All right. So I just have a couple up here, a couple rigid motions. I want to know what it is. All right, what did I do? And you can go blue to green, green to blue. It's not going to matter. All right, what did I do up here? Which rigid motion did I perform to get to one figure to the other? All right, so let's start with the first one. What are we thinking on this one here? Here we go. Let's roll. 15. That is a reflection, yes. How about the next one? What are we doing with the next one here? 5?
Rotation.
Rotation. Thank you. And then finally, what about this next one here? The final one, what are we looking at here? 17? Translation. A little sliding going on, yes. Okay, all three rigid motions. Again, what's considered a rigid motion? Any transformation that the triangles remain congruent. Oh, yes, I know you're excited when you see a graph. Go ahead, take XYZ and ABC and go ahead and graph it right now. Okay, let's answer the questions now. First one, identify the transformation. All right, you're taking ABC and XYZ is the transformation of it. So what did I do to ABC to get to XYZ here? What transformation did I just perform here? Here we go, 4. What did I just perform? This is a reflection. Nice job. And here's where we're going to put in work right now. Identify the transformation. Just did it, reflection. And verify that this is actually a rigid motion. Well, if it's actually going to be a rigid motion, what should I know about these two triangles? They're congruent. I got 5 ways to do that, but it's on a graph. So usually out of those 5 ways, I only can do it by using, or side, 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 yep, by using the distance formula, yes. Okay, so we're going to verify right now those two triangles are congruent by side, 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 and we're going to use the distance formula to match up the corresponding sides. All right, so let's take triangle ABC first. Anybody have a preference for side you want to start with? AC. Here we go. Now, you guys are in what class?
Honors.
Honors, and usually that means I'm going to tell you to do something difficult, right? but it comes with advantages. I'm just going to show you a quick shortcut here. Instead of doing all this here, I'll just show you a shortcut. If you want to take it, take it. If not, you want to use distance formula. If you want to do Pythag, that's fine. Ready? A to C. Down and over how many? Down and over how many for AC? Whoa, I'm getting a couple different answers here. We have issues with counting. Down and over how many? Down how many? 6 and over how many? 8. I just hear an 8. 2. There you go. You guys don't realize what I just did for this shortcut, but I just did Pythag. Right? Ready? I made a right triangle out of it, and I said down and over how, ready? Down how many? 6 squared plus over how many? 2 squared. And at the very end here, how do I get C by itself? I'm going to take the, boom, square root of both sides. So if you don't want to figure out, oh, this coordinate minus this coordinate, all right? This is an easier, I don't know, for me it's an easier way. Michelle? Because I have a horizontal and a vertical line. Oh, yeah. And where they meet forms a perpendicular line or 2 perpendicular lines, so that's a right angle. Right? All I'm doing is counting over horizontally, up vertically. So it's got to form a right angle. Good? All right, so here I end up with square root of 40. And yes, guess what? The other half of learning a cool trick is, yes, break it down. Biggest perfect square that goes into 40? 4 and 10. So this ends up being 2 square root 10 for AC. Next side you want to do? AB. Up and over how many? That's what I was thinking. Up 1 over. Up 1 over 4. This ends up being the square root of 17. Can we do anything with that? You let me know when you get a perfect square that goes into it. I'll just continue doing the problem. CB. And again, if you want to take this little method there for instead of distance, that's fine. If you want to use distance with the coordinates, whatever floats your boat, whatever gets the job done. You know how it goes in here. CB, down and over how many? Or up and over how many? 5 and 2. 5 squared and 2 squared will give me square root of 29. All right, let's go to triangle XYZ and hope that I have 3 distances that match the ones I've just found. Anybody want to find a side? XZ, here we go. XZ, up and over how many? Up 1 over 4 again. 1 squared, 4 squared, so that'll end up being square root of 17. 4 squared. Do we ever talk about it in here? Great game. Elementary school days. Anybody? 4 square? Man, good game. Yep. 4 squared. 4 square. Yeah. Yeah. I'm sure some of you fall into this category, but anybody ever play with kids that just start making up rules as they go along, or you might have been that kid? Like you're playing, cherry bomb, and it's like, oh, you're out, and you're like, I don't think so. Check the rule book, buddy. Yep. Just making up rules as you go along. That's why I hated that game. Where they put some spin on it, and you're like, it goes that way. Yeah. All right. YZ. What are we looking for? YZ. Up and over. Up 5 over 1 or 2. 2. I hope so. And we end up with square root of 29. We're getting there. Our last side, which is XY. Up and over 6 and 2. So that ends up being our square root of 40, which was 2 radical 10. So what do we notice here? Do I have 3 pairs of congruent sides? Yes, but we can't just leave it with the work. We got to do a little concluding statement here. So what do we know about this reflection? It's a rigid motion, all right? So it is a rigid motion. Because, how do I know it's a rigid motion? A little bit before that. What makes a rigid motion? If the 2 triangles are? Okay, so it's a rigid motion because the triangles are congruent. Now you can pipe in, Jeff, by side, side, side. Got to have congruent figures to have a rigid motion. Questions? So that's what I'm looking for when you guys verify a rigid motion, which is what you're about to do in your groups. And on your own right now. Okay, let's go. What's it going to be? We'll go backwards. Hurry up. Do you know, but I'd like you to get the practice being an honors level student. I realize that, but being an honors level student, and I'd like you to break it down. Okay, expectations are a little higher in here. What's it going to be? Stop with the swipe. It drives me nuts. Okay, fine. You want swipe? Okay, let's pick here so you can get this next problem. I got a star. I got a genie. I got a clock, which I believe already came up today. So I don't know if you want to keep with that or genie. I have genie here. I now have curtains. I got genie, curtain, star. Okay, here we go. Who wants the star? 2, 4, 6, 7. Who wants the genie? Okay, you ready for star then? Star or Promethean man? Ready? I got to go backwards, all right, because I don't have another slide. Ready? Ooh, flip. Sorry, everybody. Flip, flip. Going back. The little pinwheels. All right, go ahead. When you are done with this one, I need to see it to make sure you have the distances correct and you have identified the correct transformation. All right, so please let me see it when it's done so I can check your distances and your correct transformation.